For a 20,000 square foot school building with the following estimated demand loads, which includes lighting at 20,000 watts at 120 volts 1 phase, mechanical equipment at 100 horsepower at 480 volts 3 phase, and convenience power at 1 watt per square foot at 120 volts 1 phase, a suitable power distribution system can be designed. Firstly, the lighting load is 20,000 watts at 120 volts 1 phase. This requires a 166.67 amp circuit. Secondly, the mechanical equipment load is 100 horsepower, which equals 100 times 746 watts, giving 74,600 watts at 480 volts 3 phase. This requires a 98.13 amp circuit per phase, assuming a 0.75 power factor. Thirdly, the convenience power load is 20,000 square feet times 1 watt per square foot, which equals 20,000 watts at 120 volts 1 phase. This also requires a 166.67 amp circuit. Given the different voltage and phase requirements of the loads, the most suitable power distribution system would be a two-tiered system. This consists of a main distribution system and a branch distribution system. The main distribution system is a 3-phase 480-volt system to supply the mechanical equipment. This system will require a service transformer to step down the voltage from the utility supply to 480 volts. The branch distribution system is a separate 1-phase 120-volt system to supply the lighting and convenience power loads. This system will require a step-down transformer to reduce the voltage from the main distribution system to 120 volts. The advantages of the two-tiered system are that it provides efficient power distribution to different loads with varying voltage and phase requirements. It isolates the large mechanical load from the sensitive lighting and convenience power loads, reducing potential interference. And it allows for easier maintenance and servicing of individual circuits. In more detail, let's look at the lighting load. The calculation indicates a need for 166.67 amps at 120 volts. Standard practice dictates using appropriately sized conductors and overcurrent protection. Refer to the National Electrical Code, or NEC, Table 310.15 for conductor ampacity based on insulation type and installation method. For overcurrent protection, a standard circuit breaker or fuses can be used, selected to protect the conductors according to NEC Section 240.4. Consider using multiple circuits to distribute the lighting load, rather than a single high amperage circuit, which will improve reliability and simplify maintenance. For the mechanical equipment, the 100 horsepower motor requires a significant amount of power at 480 volts, 3 phase. The calculation shows 98.13 amps per phase, assuming a 0.75 power factor. Motor circuits have specific requirements according to NEC Article 430, including conductor sizing, overcurrent protection, and motor disconnects. The conductors must be sized at 125% of the motor's full load current rating, as per NEC 430.22. Overcurrent protection must be provided by an inverse time circuit breaker or fuses size according to NEC 430.52, considering the motor's starting current. A motor disconnect switch must be installed within sight of the motor and must be horsepower rated, as per NEC 430.109. For convenience power, the calculation results in 166.67 amps at 120 volts. Similar to the lighting load, distribute this load across multiple circuits to prevent overloading and ensure reliability. Use appropriate receptacles, typically 15 amps or 20 amps, and follow NEC Article 210 for branch circuit requirements. Ground fault circuit interrupter, or GFCI, protection should be provided for receptacles in wet locations, such as restrooms and kitchens, as required by NEC 210.8. Considering the two-tiered system, the 480 volts 3-phase system will serve the mechanical equipment, while the 120 volts 1-phase system serves the lighting and convenience power. This approach allows for efficient distribution because the mechanical equipment benefits from the higher voltage, reducing current and conductor size requirements. The lighting and convenience power are better suited for 120 volts for safety and compatibility with common devices. The service transformer is crucial for stepping down the utility voltage, which is often higher than 480 volts, to the required 480 volts for the mechanical equipment. The transformer must be sized appropriately to handle the total load of the mechanical equipment, including any future expansion. Consider the transformer's efficiency, cooling method, and impedance when selecting the transformer. The step-down transformer reduces the 480 volts from the main distribution system to 120 volts for the lighting and convenience power. This transformer must be sized to handle the combined load of the lighting and convenience power, and it should be located close to the loads to minimize voltage drop. A panel board is needed for distributing the 120 volt circuits to the lighting and convenience power receptacles. This panel board should have sufficient capacity for all the circuits, including spare capacity for future expansion. Each circuit should be protected by a circuit breaker, and the panel board should be properly grounded. The two-tiered system offers several advantages. Firstly, it improves efficiency. By using 480 volts for the mechanical equipment, the current is reduced, resulting in low losses in the conductors. Secondly, it provides isolation. Isolating the large mechanical load from the sensitive lighting and convenience power loads reduces the risk of voltage fluctuations and interference. Thirdly, it simplifies maintenance. With separate systems, troubleshooting and maintenance can be performed on one system without affecting the other. In designing the power distribution system, several additional factors should be considered. Firstly, the available fault current at the service entrance must be determined. This is important for selecting appropriately rated overcurrent protection devices, such as circuit breakers and fuses, to ensure they can safely interrupt fault currents. Secondly, the voltage drop in the conductors must be calculated to ensure that the voltage at the loads is within acceptable limits. NEC 210.19 AM provides guidance on voltage drop limitations. Thirdly, the grounding system must be properly designed and installed to ensure safety and prevent electrical shock hazard. NEC Article 250 provides detailed requirements for grounding systems. Fourthly, surge protection should be considered to protect sensitive electronic equipment from voltage surges caused by lightning or other events. Surge protective devices, or SPDs, should be installed at the service entrance and at sensitive equipment locations, following NEC Article 285. Fifthly, harmonic mitigation may be necessary if there are significant nonlinear loads, such as variable frequency drives or electronic ballasts. Harmonics can cause overheating of transformers and conductors, as well as interference with electronic equipment. Harmonic filters or line reactors can be used to mitigate harmonics. Sixthly, energy efficiency should be a primary consideration in the design. Use energy-efficient lighting, such as LED fixtures, and high-efficiency motors for mechanical equipment. Consider using occupancy sensors and daylight harvesting to reduce lighting energy consumption. Seventhly, future expansion should be planned for. Provide spare capacity in panel boards, transformers, and conduits to accommodate future loads. Consider installing a larger service entrance than is currently required to avoid costly upgrades in the future. Eighthly, coordination studies should be performed to ensure that overcurrent protection devices are properly coordinated to minimize outages. A coordination study involves analyzing the time current characteristics of the overcurrent protection devices to ensure that the device closest to the fault will trip first, minimizing the extent of the outage. Ninthly, arc flash hazard analysis should be conducted to determine the potential arc flash hazards in the electrical system. This analysis will help determine the appropriate personal protective equipment, or PPE, that is required for workers who may be exposed to arc flash hazards. Tenthly, the National Electrical Code, or NEC, should be followed throughout the design and installation process. The NEC provides detailed requirements for electrical installations to ensure safety and prevent electrical hazards. Finally, consider the specific requirements of the local utility company. The utility company may have specific requirements for service entrance equipment, metering, and grounding. Consult with the utility company early in the design process to ensure that the electrical system meets their requirements. Let's delve deeper into the specifics of selecting the appropriate equipment for the two-tiered power distribution system. For the main distribution system, which operates at 480 volts three-phase, the selection of the service transformer is paramount. The transformer's kilovolt-ampere, or kVA, rating must be sufficient to handle the total connected load of the mechanical equipment plus an allowance for future expansion. Consider the transformer's efficiency, as a higher efficiency transformer will result in lower energy losses and reduced operating costs. Also, the transformer's cooling method should be appropriate for the installation environment. Dry-type transformers are commonly used indoors, while oil-filled transformers are typically used outdoors. The transformer's impedance is also an important consideration. A lower impedance transformer will result in higher fault currents, which may require the use of higher rated overcurrent protection devices. A higher impedance transformer will limit fault currents but may also result in higher voltage drops under load. For the branch distribution system, which operates at 120 volts one phase, the selection of the step-down transformer is critical. The transformer's kVA rating must be sufficient to handle the total connected load of the lighting and convenience power, plus an allowance for future expansion. Consider the transformer's voltage regulation, as a transformer with good voltage regulation will maintain a stable voltage under varying load conditions. The transformer's noise level is also a consideration, especially in quiet environments. Encapsulated transformers are typically quieter than open-core transformers. For both the main and branch distribution systems, the selection of panel boards is important. The panel boards must have sufficient capacity to accommodate all the circuits, including spare capacity for future expansion. The panel boards must be properly grounded and must meet the requirements of NEC Article 408. Circuit breakers should be used for overcurrent protection in the panel boards. Circuit breakers offer several advantages over fuses, including the ability to be reset after a trip and the availability of various trip characteristics. The circuit breakers must be properly sized to protect the conductors and equipment they serve, and they must have sufficient interrupting capacity to safely interrupt fault currents. The conductors used in the power distribution system must be properly sized to carry the load current and to minimize voltage drop. The conductor ampacity must be selected based on the conductor's insulation type, the ambient temperature, and the number of conductors in a raceway, as per NEC Table 310.15. The conductor material should also be considered. Copper conductors offer a lower resistance than aluminum conductors, but they are also more expensive. Aluminum conductors are often used for larger feeders to reduce cost, but they must be properly terminated to prevent oxidation and corrosion. The grounding system is a critical component of the power distribution system. The grounding system must be properly designed and installed to ensure safety and prevent electrical shock hazards. The grounding system must meet the requirements of NEC Article 250, which provides detailed requirements for grounding electrodes, grounding conductors, and equipment grounding. Surge protection should be considered to protect sensitive electronic equipment from voltage surges caused by lightning or other events. Surge protective devices, or SPDs, should be installed at the service entrance and at sensitive equipment locations following NEC Article 285. SPD are available in various voltage ratings and surge current capacities, and they must be selected based on the specific application. Harmonic mitigation may be necessary if there are significant nonlinear loads such as variable frequency drives, or VFDs, or electronic ballasts. Harmonics can cause overheating of transformers and conductors, as well as interference with electronic equipment. Harmonic filters or line reactors can be used to mitigate harmonics. Harmonic filters are typically more effective at reducing harmonics, but they are also more expensive than line reactors. Energy efficiency should be a primary consideration in the design of the power distribution system. Use energy-efficient lighting, such as LED fixtures, and high-efficiency motors for mechanical equipment. Consider using occupancy sensors and daylight harvesting to reduce lighting energy consumption. Occupancy sensors automatically turn off lights when a space is unoccupied, while daylight harvesting systems automatically adjust lighting levels based on the amount of natural light available. Future expansion should be planned for in the design of the power distribution system. Provide spare capacity in panel boards, transformers, and conduits to accommodate future loads. Consider installing a larger service entrance than is currently required to avoid costly upgrades in the future. Coordination studies should be performed to ensure that overcurrent protection devices are properly coordinated to minimize outages. A coordination study involves analyzing the time current characteristics of the overcurrent protection devices to ensure that the device closest to the fault will trip first, minimizing the extent of the outage. Arc flash hazard analysis should be conducted to determine the potential arc flash hazards in the electrical system. This analysis will help determine the appropriate personal protective equipment, or PPE, that is required for workers who may be exposed to arc flash hazards. The results of the arc flash hazard analysis should be documented on arc flash labels, which must be affixed to electrical equipment to warn workers of the potential hazards. The National Electrical Code, or NEC, should be followed throughout the design and installation process. The NEC provides detailed requirements for electrical installations to ensure safety and prevent electrical hazards. The NEC is updated every 3 years, so it is important to use the latest edition of the code. Finally, consider the specific requirements of the local utility company. The utility company may have specific requirements for service entrance equipment, metering, and grounding. Consult with the utility company early in the design process to ensure that the electrical system meets their requirements. By carefully considering these factors, a safe, reliable, and efficient power distribution system can be designed for the 20,000 square foot school building. The two-tiered system with a 480 volts 3-phase main distribution system and a 120 volts 1-phase branch distribution system provides an optimal solution for meeting the diverse power requirements of the building's various loads. The selection of appropriate equipment, including transformers, panel boards, circuit breakers, conductors, and grounding systems, is critical to the performance and safety of the power distribution system. Adherence to the National Electrical Code, or NEC, and consultation with the local utility company are essential for ensuring compliance and preventing electrical hazards.